All right, so where does this leave us? Well, this gets us to the photoelectric effect. And now that we know basically what has to happen to liberate electron, we can consider the experiment. Now, I hope you remember in your notes, we've already talked about what the photoelectric effect is, and it relates to the energy it takes to remove an electron from a metal. And I'd like to show you how easy actually this is to measure, relatively speaking. All right, so this is the photoelectric effect. Okay, so here's the experiment. And I'd like you to be able to explain this to someone else as well. It's pretty simple. We begin with a cathode, which is really just a piece of metal that is going to be where the electrons in our experiment come from. Then we have an anode, which is just a piece of metal that is going to receive the electrons. And these are arranged within some short distance from each other, and then these are connected to a voltage source. Okay? So these are metals that are arranged in a kind of parallel plate capacitor situation. All right, and then in between is an insulator. So if this is all we have, then how much current is going to go through here? Well, of course, at least in the ideal case, nothing, right? No matter what the voltage is over here, the flow of electrons or the current itself is going to be 0. All right, so we'll give this the label of V sub 0. All right, now if we have some light shining on this from a light source, which I'll draw as a big box, well, then, under some circumstances, some electrons can receive enough ionization energy to jump out from this cathode and be collected toward the anode. Now, why would they, we just talked about the ionization energy, so we know why they might leave the cathode, but what would draw them up toward the anode? Well, that's pretty simple. If we have this situation, then we know that we have an electric field, right? Just by the geometry of this. If we have a potential difference here, then that's going to set up an electric field. And in this particular polarity, then we have a positive voltage on this side, a negative voltage on that side, and then of course any negative charge that winds up in between these two is going to travel toward the anode. All right, and so when these electrons appear, it leads to a current, and that current is called a photocurrent. So electrons by the cathode are attracted to the anode because of the electric fields we just talked about, and this process is what we call a photocurrent because it's only happening because of the light source as well as the other things showing up here. But these are electrons that need the photons to be liberated from the cathode. All right, and then of course these electrons can come all the way to the anode and then lead to an actual current, a photocurrent. Okay, very interesting. What if we flip the polarity? Well, in that case, we would expect then the negatively charged electrons to flow the opposite direction, right? So if we instead had a second case where we inverted this is case 1. So if we inverted the polarity, then of course the electrons would be directed, any liberated electrons would be directed back into the cathode, and then there would not be any current through the loop. I hope that kind of makes sense to you. And at the very least, the photocurrent would decrease. All right, so if we look then at what the IV curve from this is, then we would see something like this. And this is a plot of voltage and current. Okay, well, first we know that if we have light intensity, if we have a low light intensity, let's say it's a dim light, well, it turns out that at some negative voltage, which is not 0 generally, but at some negative voltage, the electrons that are emitted from here are going to be so repelled by the negative voltage here that they're not going to lead to any current at all, and none of them are going to lead to the anode. So that's some negative voltage here. And we're going to, I guess, identify this as V0, and I've used V0 on these illustrations, but we should remove it. So that subscript should be removed. It's just V, and then I, and then of course V and I. And so this is the applied voltage, or the bias voltage. Okay, so there is some negative voltage at which there is absolutely no photocurrent. And then as we increase the voltage, it goes up, 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 up. And then at some point, which is the 0 voltage, the current does not increase anymore. And if we have more light, then this slope gets higher. All right, so this is what happens for increasing light intensity. All right, so for increasing light intensity, this is what we see. All right, well, that's very interesting, I suppose. But there's one other thing, and I guess not just interesting, but this tells us, of course, that if we have more photons coming in to our capacitor, then we're going to get more electrons. And I guess that's not all that surprising. But there's one other thing that's really important that we haven't talked about yet, is that if we go back here, if we look at this, these electrons, they are not just emitted and then hang out somewhere close to the cathode. They actually leave the cathode with some energy, with some kinetic energy. And so they actually have kinetic energy that's proportional to the frequency. And that's why we have a voltage here that is going to be different for different frequencies. All right, so for one frequency, it's going to lead to one, and for another frequency, it's going to lead to the second one. All right, and so what does it mean? Well, it means that regardless of light intensity, the photocurrent that results, there will be a 0 point for a given frequency where the photocurrent is 0, no matter what happens. And at this voltage, every emitted electron is repelled from the anode, and we can then find the kinetic energy is proportional to the charge of the electron times the voltage, this V0. And because that then must be the maximum kinetic energy, and in this at that point, the energy of the potential field is just strong enough to prevent any electron from reaching the anode. All right, and this point is not dependent on intensity. But if we change the frequency, we get different bias voltages. All right, we've covered a lot of ground, but I'm coming in for a landing, so stay with me. So what does this all mean? How do we put this all together? Well, first of all, it means something about the relationship between the photoelectrons and the frequency of the photons that produce them. And let's summarize that here. And by the energy of the electrons, what I want to identify is that the kinetic energy of those electrons that come off the metal surface will have a kinetic energy that we can relate back to its velocity. But we can also relate it back to the potential times the charge. And of course, in the electrical measurements, what we talked about here with this photocurrent versus a bias voltage, we can measure this V naught, and of course we know the charge of an electron. All right, so if we then map what we find from this experiment, we see that there's a line, a linear relationship between the energy or the bias voltage, V sub 0, where it all comes down to all the lines converge, that's this over here. There's a linear relationship between that voltage and the frequency of the light that produces it. And at that frequency, well, I'm sorry, let me say this is a particular frequency where the kinetic energy becomes 0. And below that F naught, there is this kind of frequency threshold. And below that, there are no electrons that come off with any energy whatsoever. And it is this threshold, or this region of this experiment, that leads us to know, first of all, that, that photons have a particle nature. And notice that this F naught is for the metals of interest in this experiment, not 0. And so the fact that this is not 0 tells us that there is a minimum amount of energy that is needed in order to produce the photoelectrons, combined with the fact, of course, that no matter what the intensity is of the light shining on the metal, this is the same relationship or the same kinetic energy on those electrons. So adding more intensity doesn't make the electrons any more energetic. Now, the second thing that it tells us is, of course, that the atomic orbitals are quantized. All right, so this relatively simple experiment is one of the earliest experimental demonstrations that show these two aspects, and they're actually pretty simple. And finally, I'd like to point out that the slope of this line is actually equal to Planck's constant. And why is that? Well, it turns out that the energy of a photon can be written as Planck's constant times its frequency. All right, well, that's it for the photoelectric experiment.